Okay, welcome. So this is the second session of Module 2. So tonight we're going to keep talking about limits. We talked about limits in the last webinar. This time we're going to talk about infinite limits and another approach to dealing with other types of limits. We're going to talk about continuity. We briefly talked about it in the last webinar, and then we're also going to talk about the intermediate value theorem. So let's get started. So there's something called the sandwich theorem. And the sandwich theorem basically is used when there's several cases where it's used, but the idea is if I have a function f of x, and there's a few cases, say I don't know what that function is, or I know what that function is, and taking the limit of that function isn't something that's easy to do. What I can do, if I know g of x is less than or equal to f of x, and I know h of x is greater than or equal to f of x, then let's say taking the limit of those two is something I can fairly easily do. Then I can take the limit of those two functions as x approaches a. So that's what this says. If I take the limit of g of x as x approaches a, and I take the limit of h of x as x approaches a, and I get the same thing, let's say L. So for example, 3. Let's say we take the limit of those two functions and we get 3. That means that the limit of the function f of x also is 3, or L. So there's a few different cases where that's useful, and we're going to talk about one of those towards the end. So we will do an example in a minute, but we'll also come back to this a little bit later. So here's an example of the sandwich theorem. It's also known as the squeeze theorem, so you may have heard it both ways. So find the limit given we have 11 minus 5x squared over 2 plus x is less than or equal to f of x, and that's less than or equal to 11 minus x squared over 2 plus x. The idea here is we don't know what f of x is. We weren't given that information, but we do know a function that's smaller and a function that's larger. So we can take the limit as x approaches 0 of those two functions, and if they're the same thing, we can assume that that's the limit of our function. If they're not the same thing, we can't conclude that. So let's take the limit as x approaches 0 of the lower function. So 11 minus 5x squared over 2 plus x. Can we use a direct substitution here like we did in some of the examples in the last webinar? Good, we can. The only place we'd have any issues is at x equals -2, and we're not taking the limit as x equals -2 or approaches -2. So we can do a direct substitution. So I have 11 minus 5 times 0 squared over 2 plus 0. So I get 11 over 2. Now let's take the limit of the other function, the larger function. So we have 11 minus x squared over 2 plus x. And again, we have the same denominator. The only issue that we would come across would be when x equals -2, but our limit is approaching 0. So we can do a direct substitution again. And do we get the same thing? We do. We get 11 over 2 again. So the idea is, because those two functions, one's above and one's below, have the same value, that means that the function in the middle, f of x, also shares the same limit. And like I said, if we had two different values, we couldn't make this conclusion. But because they're the same, we can conclude that our function is also 11 over 2. The limit as x approaches 0. And we were given that f of x is between those two functions here. It's possible that we would be given a case where we aren't told that. And we'll, like I said, we'll come back to that later on in the webinar. But that's another approach. If we weren't given f of x, or if we were given a function that doesn't have an easily calculated limit, we might be able to use the sandwich theorem. Okay, so let's talk about continuity. So we've talked about continuity a little bit in the last webinar. Basically, continuous function is a function that does not have any breaks in the graph or any holes in the graph. So we looked at a few examples last time that had things like this. We had filled in circles, something like that. This is discontinuous. We've got like this. The hole that's in the graph, that gives us a discontinuity. So these are two examples of a discontinuous graph. So to be continuous, there's three criteria that have to be met. The first is that, it doesn't really matter what order, but to be continuous at C, let me go ahead and write that. To be continuous at C, and C can be any value, the limit of the function as x approaches C must exist. So we had a few in the last webinar where we had an answer of does not exist. So that's one of the criteria. To be continuous, all of these criteria have to be met. Another part of this is that f of c. So if I just plug in c into the function, it also must exist. So for example, if this was c on the graph that I drew earlier, f of c doesn't exist because f of c would be right here and there's a hole in the graph, which means that doesn't actually exist right there. And the last criteria is that those two have to be the same. So the limit as x approaches c of the function f of x has to be the same thing as if you just plugged in c for the function. So the direct substitution worked, basically. So like we talked about in the last webinar, polynomials are continuous everywhere. And that's because I can always use direct substitution when I plug in, say, c to the function, because there's no issues with polynomials. We won't get a hole in the graph or any sort of asymptote. So that's more of the formal definition. Basically, to be continuous, there just can't be any breaks or any holes in the graph. So let's do some examples. So at what points is the function continuous? Well, sometimes it's easier to think about what points is the function discontinuous. And where would this function be discontinuous? How could we figure out where it would be discontinuous? Well, we could graph it, but that's not always an easy way to do this. Very good. So we can set the denominator equal to 0, because when the denominator equals 0, that's where we have a discontinuity. So this function is discontinuous when the denominator, so x squared minus 13x plus 30 equals 0. And it's continuous everywhere else. So what we can do is we can factor this, just like we did in the last webinar. So I always draw my two parentheses, still equals 0. I have an x and an x. I always keep the first sign, so what is the second sign going to be? So we have a positive 30, and we already have a negative, so a negative times a what would give us a positive? Good. And we need factors of 30 that will give us 13. So 10 and 3. Very good. So now I can set both of those equal to 0, so I can kind of break it apart and say x minus 10 equals 0. This is where it's discontinuous. And x minus 3 equals 0. So that means x equals 10, there's a discontinuity, and x equals 3, there's a discontinuity. So we wanted to know the points where the function is continuous. So we know it's discontinuous at 10 and 3. So the way to write this is, there's a few different ways to write this. Typically you would write this in interval notation. So the easiest way for interval notation is if you draw a number line, here's 0, here's 3, and here's 10. I usually just write 0 just to give me an idea of where to draw the other numbers. We can't be 3 and we can't be 10, but we can be everything else. So I just need to write all of the intervals that we can be. So this kind of goes back to the first module, or the first webinar. So the first interval is from negative infinity up to 3. And we would use a parenthesis, because remember the bracket represents being included, and if we can't include 3 because that's where it's discontinuous. And then we use the union, and then the interval from 3 to 10. And again a union, and then the interval from 10 to infinity. So that is all of the points where the function is continuous. The only place that there's any discontinuity would be at 3 and 10. So it's continuous otherwise. And they all get parentheses because infinities always get parentheses, and 3 and 10 can't be included, so they would get parentheses. Okay, let's do another one. Going back really quick, I do want to mention, sometimes you might see this as continuous when, and you would have a not equal to, not equal to. That's just if you said it's continuous when x is not equal to. It's the same idea, just the opposite direction. So you could do that either way. What about this? At what points is the function continuous? What do we think? Very good. It's always continuous because, one, we have a polynomial, and for any value of c, going back to the definition of continuity, for any value of c, there is the value of the limit as x approaches c is always going to exist, and it's going to be the same thing as just direct substitution of f of c. So in this case, it's a polynomial, so it's continuous everywhere. And more formally, if we wanted to write the interval notation for where this is continuous, because it's continuous everywhere, it's the entire number line. So we would write it as negative infinity to infinity. There's no places where we would have any sort of 0 in the denominator of a fraction or anything like that, because we have a polynomial, so that's not possible. All right, let's go to the next one. So I want us to find the values for a and b. So a and b are some constants, some numerical values that will make this function continuous. So we have a piecewise function. Piecewise function, again, just has different parts of the graph, and what we're wanting to do is we're wanting to make this so that it is continuous. So a piecewise function could look something like this. But that's discontinuous. So the idea is I want to make it so this piecewise function is continuous, which means I just basically want to join all of the parts together. So if we look at the first two, parts of the piecewise function, -6 and ax plus b. How am I going to ensure that those two have no breaks in the graph, or no holes? Well, what I could do is I could set them equal to each other, because that would mean that they would have to be the same value, which means that they can't have a break. So I would have -6 equals ax minus b. What x value would these two parts of the piecewise function come together? Do we know that? Well, this one ends at -3, and that one starts at -3. So the idea is at x equals -3, in order to be continuous, we want those two to be equal to each other. So at x equals -3. So I set them equal just because I want this to be continuous, so I don't want any breaks in the graph, so I don't want this. I want them to be continuous, which means at x equals -3, where the first part of the function ends and the second part begins, which is x equals -3, I want them to be equal. So putting that together, I can plug in x equals -3. So I'd have -6 equals -3a. I plugged in a for x, and so I just moved the -3 to the front, minus b. So all I did there was I just plugged in x equals -3. The problem is I have two unknowns in this equation. I don't know a and I don't know b. So in order to solve an equation with two unknowns, I need another equation. I need one equation for each unknown. So what can I do? I've got one equation. Well, I can do the same thing with the second part of the piecewise function. I can say where I want them to join together, I need them to be equal. And where do these two, what x value do these two need to be joined together? Well, this one ends at 1. Good, 1. This one ends at 1, and this one starts at 1, which means that x equals 1, I need those to have the same value so that if they're equal, that means there's no break in the graph. So because that one ends at 1 and the other one starts at 1, that's where I want them to be equal. So at x equals 1, I want ax minus b to equal 4. And then we can do the same thing that we just did. We can plug in x equals 1. So I have a minus b, when I plug in 1 for x, equals 4. So now I have equation 1 and equation 2. So I have my two equations and two unknowns, and I can use a system to solve this. And we'll do that in just a minute. Are there any questions so far? Okay, so just to recap, I need these two to be equal to each other at x equals -3, because that's where one ends and the next one begins. So if they're equal, then there's no breaks in the graph. And I had to do the second part because I needed another equation to solve for a and b. So I do the same thing. At x equals 1, this one ends, and at x equals 1, this one begins. And so that's where I need those two to be equal to one another. So let me go to the next page. So I have -6 equals -3a minus b. That was equation 1. All I've done is I just put the negatives. Actually, I didn't move anything. I am going to rewrite the a minus b equals 4 as 4 equals a minus b. It's not really necessary. I just usually like to line up if I can. So there's a couple ways we could solve this. We could use the substitution method, or we can use the elimination method. Either approach works. So basically the idea is, in this, I'll just use the substitution method. I'm going to solve one of these equations for one of the variables. So for me, looking at equation 2, if I were to add b over to the left, I would have 4 plus b equals a. So all I've done is just solve equation 2 by moving over the b. What can I do with that? Good. I can plug a is 4 plus b into the other equation. So I have negative 6 equals negative 3, and I'm just replacing a by 4 plus b, and then minus b. So now I have one equation with only one unknown variable, and that's b. So when I distribute, I have negative 6 equals negative 12 minus 3b minus b. So the negative 3 gets distributed to both. So then I have negative 6 equals negative 12 minus 4b, and I need to solve for b. So I will add the 12 over to the left. So I get 6 equals negative 4b. And then I can divide the negative 4 on both sides. When I simplify 6 over 4, I end up getting 3 over 2, and we have a negative from the negative 4, so negative 3 over 2. So I have one of the values that I was looking for. How am I going to get the other one? Very good. You can plug it into equation 2. You could also plug it in where you've already solved for a. Either way, you're going to get the same answer. So I draw lots of arrows with these types of questions. I have 4 plus b, which is minus 3 over 2, equals a. So all I've done is I plugged b in for b, and the 4 plus b equals a. And I get a equals 5 over 2. You can rewrite 4 as 8 over 2. So then 8 over 2 minus 3 over 2 gives us 5 over 2. So if a is 5 over 2 and b is negative 3 over 2, that will make this piecewise function continuous. Okay. So depending on how the question's asked, in this case it was just asked for find the values of a and b, so leaving it as, let me go to the next page, a equals 5 over 2 and b equals negative 3 over 2. That would be one. Again, it depends on how the question was asked. You could also be asked to rewrite f of x, so you would write f of x just replacing a and b as what they are. So you would have negative 6 when x is less than or equal to negative 3. And you now, for your second equation, is ax minus b. So you'd have 5 halves x minus 3 halves, minus b, so minus 3 halves, minus negative 3 halves. You could write that as plus 3 halves. Between negative 3 less than x is less than 1, and then 4 when x is greater than or equal to 1. I am going to go ahead and simplify that negative negative into a positive. So either one. Likely my MATLAB would ask you to write A and B and give you a blank for each of them, or they would ask you to rewrite it as f of x in the way that we just did. Okay, so infinite limits. We had a couple examples in the last webinar where we ended up getting an infinite value for the limit, or the limit, the graph heads towards infinity. But what about if we were taking the limit as x approaches infinity? The first thing that I want us to think about before we start with this question is infinity. Infinities are not necessarily all the same size. So think about it this way, 2x as x goes to infinity. And then if we had 2x squared as x goes to infinity, 2x squared is larger. So as x goes to infinity, that value is going to a larger infinity than just 2x. But we just call it infinity because infinity, or 2x infinity, is still, or 2 infinity is still an infinite number. So why I'm saying that is because if we try, we can't think of infinite limits in the same way that we did with numerical values. So I can't plug in infinity as I would a number. In the numerator, as x goes to infinity in this question, where is the numerator going? Well, we have a negative infinite number and a positive infinite number. They don't cancel each other out because they aren't necessarily the same size infinity. And in the denominator, we have an infinite number minus 5, which is still an infinite number. So those don't cancel out in ways that numerical values do. So I can't think of it that way. Again, before we go there, what if I asked us to find the limit as x goes to infinity of, let's say, 1 over x? Going back to the last section that we were, or the last webinar, we can't plug in infinity because it's not a number. But what can I do? Well, I could choose, very good, I could choose larger and larger x values, kind of like how we chose numbers closer and closer to 0 in the last webinar. We could say, let's plug in 1 over 10,000, for example. I'm just choosing a large x value. This is what I would get. But 10,000 is not infinite. So let me choose another number that's even larger than 10,000, heading towards infinity. So let's say I plugged that in. This is what I would get. So as I choose larger and larger and larger x values, so as x goes to infinity, 1 divided by larger and larger values is getting smaller and smaller and smaller. So it's getting closer and closer to 0. So the limit as x approaches infinity of 1 over x is 0. I have 1 divided by an infinitely large number. And that's going to be a very, very, very small decimal. And the same idea happens even if there was a 5 over x, or any constant in the numerator. I have a constant divided by an infinitely large number. It's going to be a very, very small decimal, close to 0. The reason I mention that is because it helps us to solve something like this. If I can get each term in some way similar to 1 over x or something like that, I know the limit of 1 over x goes to 0. So the easiest thing to do, let me see if I have another page. Oh, good. Let me rewrite the limit here. I basically want to try to get each one of these terms in some form of 1 over x or 1 over or any constant over something x related. So what I'm going to do is I'm going to divide each term by the largest exponent or the largest term in the denominator. And the reason I'm going to choose the denominator, and I'll always choose the denominator, is because I don't want to end up with 0 in the denominator. So by me dividing each term by the largest, so in this case x squared, because that's the largest x term in the denominator, by me choosing that, I'm going to ensure that I end up with a 1, and you'll see in just a minute what I mean. So let me divide each term by the largest value in the denominator, which is x squared. So I have the limit as x approaches infinity. That's still here. We haven't dealt with the limit yet. So I have negative 3x squared over x squared. So I just divided each term. Plus 2x over x squared. Over 9x squared over x squared. Minus 5 over x squared. And you may be thinking, why am I allowed to divide everybody by the largest term in the denominator? Basically what I'm doing is I'm multiplying the numerator by 1 over x squared and also the denominator by 1 over x squared. So what am I actually multiplying the function by? 1. Good. So I'm not changing anything by multiplying the function by 1 over x squared over 1 over x squared. It's just multiplying by 1, and I can always multiply by 1. So let me simplify each of these terms now. The limit as x approaches infinity. Still there, we haven't taken the limit yet. In the first, the negative 3x squared over x squared, the x squareds cancel, so I have negative 3. What does the second term become? Two over x. One of the x's, the 2x one, that x cancels, and then there's still one x in the denominator. And then in the denominator, I have 9 because these x squareds cancel. And then 5 over x squared I can't do anything about, so minus 5 over x squared. So as x goes to infinity, negative 3, there's no x with negative 3, which means that term is not affected. So what about the 2 over x? What happens to 2 over x as x goes to infinity? Very good. It goes to 0. It's going to get smaller and smaller, just the same way that the 1 over x did. The same thing happens as right there. So it's just now the numerator is 2. So this term goes to 0. And the 5 over x squared. Does the same thing happen again? Yes. We have an x squared in the denominator. So basically we're taking that infinitely large number, we're squaring it, so it's becoming an even larger number. And we have 5 divided by that. So this is also going to 0. So all that we have left is negative 3 over 9, or negative 1/3. So the idea is if I can get each term to some form of a constant over an x term, then when I take the limit as x goes to infinity, those terms are going to go to 0, and the only thing that will be left is any constants that didn't have an x after we divided each term. So now we have the limit as x approaches negative infinity. The only thing that changes here, it depends on what you're working with, but I want us to think about this, the limit as x approaches infinity, negative infinity. of our original example, 1 over x. How does that change when we said we can't plug in a negative infinity, it's not a number, but let me choose some very large negative number. So let's do the same one that we just did. Let me choose 1 divided by, it's going to negative infinity, so negative 10,000. That was the first one that I did before. What does our answer end up being? It's the same 0.0001, it's just negative now. And I chose negative 10,000, and again, I can't plug in an infinity or a negative infinity, but I chose a large negative number. And now I'm going to choose another large negative number, an even larger negative number. So the only thing that changes is now we have a negative value. So negative 6 zeros. So is anything really changing? No. Good. 1 over x, as x goes to infinity or negative infinity, the only difference is that it's going to 0. It's just going to 0 from the positive side versus from the negative side. It's still going to 0 though. So this still equals 0. That doesn't mean that when we take a limit as x goes to negative infinity, it will always be the same as positive infinity. It just depends. So this case, we have the same example that we had in the last one. I want us to do the same thing that we did before, where we divide each term by the largest term in the denominator. And I just choose the x terms. You could also divide each term by a 9x squared if you wanted to, the entire term. It works out the same way. Just going to rewrite the same question. So let's divide each term. I just wrote an x to the 5th rather than an x squared. Sorry about that. So let's divide each term by an x squared, or again, if you want, a 9x squared. It works out the same way. So when I divide out the x squared, I get negative 3, the same thing I did in the last case, plus 2 over x over 9 minus 5 over x squared. So even though x is approaching negative infinity, it's still a very large negative number, which is still making 2 over x go to 0. And it's still making 5 over x squared go to 0. So we still end up with the same thing. So the reason again that I chose the denominator is by me dividing out the x squared, I'm ensuring that whatever that coefficient that was in the denominator, in this case is a 9, it's going to stay there, which means that we won't end up with a 0 in the denominator. So let's say we have the limit as x approaches infinity of 2x squared plus 5x over 9x to the 4th minus 4x squared. Again, we can't plug in infinity as we would a 5 or something similar, but we can do what we've been doing. And what do we think? So the largest term in the denominator, good, is an x to the fourth. So I'm going to divide each term by an x to the fourth. So I always want to choose the largest term in the denominator. So it's the same thing as multiplying by 1 over x to the fourth over 1 over x to the fourth. That's why we're allowed to do this, because I'm not changing anything, I'm just multiplying by 1. So I have the limit as x approaches infinity of 2x squared over x to the fourth, and you don't necessarily have to write this step, just mostly writing it for notes, plus 5x over x to the fourth over 9x to the fourth over x to the fourth minus 4x squared over x to the fourth. So I just divided each term by an x to the fourth. And what I end up with, when I simplify, I have the limit as x approaches infinity of 2 over x squared. The x squared cancels and leaves an x squared in the denominator, plus 5 over x to the third over 9 minus 4 over x squared. And now, any term, we have 2 divided by x squared, and as x squared goes to infinity, we have 2 divided by an infinitely large number. So that goes to 0. 5 over x to the third goes to 0. Good. 4 over x to the fourth goes to 0. 4 over x squared goes to 0. So we're left with 0 over 9. Remember, the only time we really have any problems is if we end up with 0 in the denominator, but 0 divided by 9 is just 0. Okay, so dividing each term by the largest term in the denominator, it will ensure you don't get a 0 in the denominator. And it gets these fractions in each term, or a constant, and we can take the limit of those individual fractions, and those, if we have 5 over x or 2 over x squared, those go to 0 as x goes to infinity. Okay. Let's move on. I want us to find the limit of sine x over x. And there's a couple different ways we can do this. The limit of sine x over x. Well, as x goes to infinity, in the denominator, we're going to have an infinitely large number, but the numerator, as x goes to infinity, sine x, if you think in terms of what the graph of sine x does, it doesn't tend towards one number at all. What does sine x do? Do we know anything about sine x? Very good. Sine x goes between 1 and negative 1. So I know that sine x is between 1 and negative 1. So as x goes to infinity, we don't have one answer, which means it doesn't exist. But what can I do with this? Does this look familiar? Well, going back to the very beginning, good, yes, the sandwich theorem. Going back to the very beginning, I have that sine x is between negative 1 and 1, and I need sine x over x. How can I get that? Well, I can divide each term by x, which I could do. There's two situations here. If x was negative, it would flip the inequality signs, but it would flip both of them. So sine x over x would still be in the middle of the two terms, and it would still be okay. So I have negative 1 over x is between sine x over x, just rewriting the line up above, and 1 over x. And now what I can do is I can take the limit of the two outside functions, and if it's the same value, then that's the value of our limit. So I have the limit as x approaches infinity of negative 1 over x. What does that go to? Good. It goes to 0. If I choose infinitely large numbers for x, and I divide negative 1 by those infinitely large numbers, I'm going to get a negative number, but it's a negative number that's getting closer and closer to 0. What about the other side? Good. It will also be 0. So that means that I can conclude that the limit of sine x over x also goes to 0 as x approaches infinity. So in the first example that we did with the sandwich theorem or the squeeze theorem is we were given the two outside functions and not given f of x. In this case, we're given our function that we're trying to take the limit of, but we can't take the limit of it directly. So what we can do is we can build two functions, one that's larger and one that's smaller, and then I can take the limit of 1 over x and negative 1 over x fairly easily. Okay. So the intermediate value theorem. If I have a function that's continuous, so there's no breaks in the graph, on a closed interval AB, closed interval just means on some interval AB, including the endpoints. And C is some value that's in between A and B, anywhere. So C could be right there, or anywhere in between the two. If f of x is continuous, meaning again there's no breaks in the graph, then there is some value. Why not? Just the notation. That is between f of a and f of b. Basically, if there's a so how we can use this is if we're trying to determine the solutions to an equation or how many solutions there are, for example, we can use the intermediate value theorem. So again, if we have some value c that's somewhere in between a and b, then the y value at that point is somewhere in between the y values at the points a and at the points b, or at the point a and b. That's all it's saying. So I want us to use the intermediate value theorem to show that there are three roots to the function below on the given interval. So we have f of x equals x to the third minus 3x plus 1. And our interval is between negative 2 and 2. So we could graph this. And what does it mean to say there are three roots? What is a root? Well, a root is just the x-intercept. It's where the graph crosses the x-axis. What's the y value on the x-axis? Do we know? Very good. So a root, or a zero, another word for root, is 0. Or solution, or x-intercept. So on the x-axis, we know that y equals 0. How is this useful? Well, we're trying to show that there are 3 roots to the function below on the given interval, meaning somewhere between -2 and 2, this graph is going, or this function is going to cross the x-axis 3 times. Ideally, we would just solve it by setting it equal to 0. But the problem is this isn't something that factors very nicely. So factoring it or solving it isn't nearly as easy. But what we can do is I can plug in all of the values on the interval. So I can find f of -2. So if I plug -2 into the function, I'm going to get a value of -1. So at -2, the graph is below the x-axis. But then if I plug in -1, so I'm just moving across the interval between -2 and 2, what do I get? I get the value of 3. So what does that mean? Can we make any conclusion about that? Basically what it means is at x equals -2, the function is below the x-axis. Because it's a -1, so I know it's below the x-axis. But at x equals -1, we have a value of 3. And I know 3 is above the x-axis. Very good. So I can conclude that somewhere between -2 and -1, the graph crossed the x-axis, which means there is a 0. So I know that there is 1, 0. There is a 0. Between -2 and -1, because it crossed the x-axis somewhere between there. We don't necessarily know where, but we weren't asked for that. We were just asked to show that there are 3 roots. So we can do the same thing with the other values. So I can plug in. I can do the same thing. I can find, and I'm just going to keep going along the interval, f of 0. When I plug 0 in for x, I get 1. And when I plug 1 in for x, I get -1. So that tells me that this function, again, crossed the x-axis somewhere between 0 and 1, because it was above the x-axis function. And now at x equals 1, it's below the x-axis because we got a negative number, which means it's below the x-axis, which means somewhere between the two values, this function has crossed the x-axis. So that means there's another root or another 0. Good, so we have to find one more. So let me just write, there is another 0. Well, I'll call it root because the question called it a root. They're the same thing. Root between x equals 0 and x equals 1. So far we found that f of negative 2 is negative 1. We found f of negative 1 is 3. We found f of 0 is 1. And f of 1 is negative 1. So from here to here there was 1, 0. From here to here, nothing happened. But from here to here there was another 0. Is there any other points that we have left to check? Good, 2. And I just said I would call it roots, and then I called it zeros again. Sorry, they're the same. I keep using 0 though. Now I can check f of 2. When I plug in 2 for the original function, I get 3. So the graph has gone from negative 1 to 3, which means, again, it had to cross the x-axis somewhere in between 1 and 2. Which means I get another 0, or the third 0, or root. So we can conclude that there are 3 zeros, or roots. So this function had to cross the x-axis 3 different times. So again, and how did I know that this was continuous, by the way? Because remember, the intermediate value theorem says that the function has to be continuous on the interval. Good. We have a polynomial. So any interval that we would have been given, it would have been continuous. And we could have had a rational function as well. It's just that the interval would not be able to include where the discontinuities are. But we could still use a rational function. And I believe that is it for Module 2.